Okay, we'll get started. So first I go through a quick summary of my last lecture. So last lecture we discussed this feed-forward network. It's basically a network that has no loops. The connection just go in one way. Because my last lecture actually covered lots of material, so now we just give a brief summary. If you have any question, I'd like to answer a question about this last lecture. All right. So the simple neural model we used, it is based on like a firing rate model. It's not individual spikes. It's much simplified. The simple network is called a perceptron, just a linear summation of inputs, right? And then this simple system can learn to classify different patterns. And there's a simple learning rule, right? It is like a HAB rule that we can discuss more today. And it can be derived by very standard techniques called gradient descent on some error function. So that basically shows you how to change the parameter of your model, which is the weights, to minimize some error between the desired output and actual output. It's a very standard method for machine learning. It's not the best, but it's the simplest one. And there's a limitation of such network, right? It cannot separate things. If you cannot separate different category of input by a line in 2 dimensions or hyperplane in high dimension, then the system will not work. No matter how you change the learning rule, it doesn't matter. And so one thing we talk about a little bit detail is called optimal linear mapping. It's basically like a 2-layer perceptron, multiple inputs, multiple outputs. Right? You want to find a way such that you map your input to the desired output as closely as possible in the sense of least square. Right? So that turns out the solution is the same as a perceptron solution. Right? Once you reach the minimum of error, that's actually exactly the same. So the interesting property, right? This is I'm not sure. Have you already done your homework yet? If you play with that, you see that if you have a corrected input or some damage to our system, the system sort of still works. Right? So if you play with that, you may already wonder what happens if if I give it the correct input, I pass through network, get output. So output will look better than the correct input, closer to the actual output, to the desired output, but slightly some more noise. But what happens if you use output and use that as an input to the system and fit into a system again, try to iterate, right? Eventually you get much better stuff, right? So that's already a recurrent network, there's a connection going back in loops. So that's what we're going to talk about today. So of course we know the multi-layer perceptron is just like many layers of the simple perceptron. You add some nonlinear input-output transformation, and have up. So the system is much more powerful. As we said that in recent years, the so-called deep learning or deep networks, they are basically winning all the competitions in artificial intelligence. They try to recognize different patterns, recognize people, recognize objects, do all kind of stuff. They are winning pretty much all the competition. So this is the state-of-the-art system to do that kind of work. It's kind of very amazing, right? In the sense that we only borrowed a little concept from the brain, not too much, just a little bit, which it already works, so it's just fantastic. It's just amazing. All right, so any questions about this thing so far? Okay, so I'll go to the next topic about this recurrent network. So the recurrent network is different from feed-forward network in many different ways. The first thing is that if I give a feed-forward network, I give you an input, of course there's output, that's very simple. But sometimes you can have a single input, there are many different possible outputs. That's not possible with a feed-forward network because the input-output is just one-to-one mapping, very simple. But if you have a recurrent network, you have internal dynamics. So you give us, depending on initial state, the system may settle in different output states. Right? of course, it can have oscillation. That's not possible with feed-forward network. And so today I'm going to talk to you in detail about this so-called half-field network. Half-field is a Zhang half-field. We invented this stereotypical current network that works like a magic. I'm going to show you in a minute. Sorry. So let's first talk about some property of recurrent network. Like what we mean by one input and multiple output. Right? This is if you imagine you have two neurons, right? They are inhibit each other. Like try to push each other down, and then there's some kind of input to them. Then one of them may win the computation. So this is just like the basic concept. Then you can imagine the system may have two different outputs, like a push-pull kind of circuitry in electronics. Right? The system allows two stable states. Either one may win the computation. If that's the case, then this can explain some stuff look like this, like the ambiguous figures. If those things are very famous. Right? This is the simplest one, called the Necker cube. So if you stare at this for long enough time, you may look at it two different ways. Maybe the first percept that you see this shape here, this is the sort of bottom of a cube. Right? If you look at it long enough, you may think about what's the way to look at it? But there is another way to look at it. This is a sort of this thing instead of it's a parallelogram. It's not in the bottom, but it is a wall. Right? You may look at it from above, and this square is the bottom of the square. That's possible. There are more than one way to look at this stuff, right? So the thing about this is that if you look at it long enough, your percept will switch spontaneously. The people think that you can control which way to switch. Actually, you cannot. Unless you control the eye movement, right? This thing will spontaneously switch. So the things that you have it's basically one input. It's the same input, but the output is different. So that means there must be something happening in your head, probably a different network competing against each other, different percepts competing against each other. Right? This is just one input and multiple possible outputs. Of course, this is the sort of stuff. This is like England is the Queen Elizabeth, right? That's the Prince Philip. That's his husband, her husband. So these are two different percepts, either as a vase or at the faces. This is another sort of my wife or mother-in-law. It's like either you see the cheek of a young woman, it's eyelashes, or just the old woman is the little mouth and nose. Right? That's two different. It's the same input and multiple output. That's actually possible. So what happens in the brain when you have multiple outputs? So here's one example. There are several experiments like this, but this is a sort of one example that shows you in the real experiment. In this, they use the binocular rivalry. You all look at the stereoscope. You have two lenses. You look at two pictures. They're just slightly different. Like shot by camera with slightly different angle, then you see a three-dimensional object, right? So two images will fuse in your eyes. We all seen that in a sort of 3D movie. So what you don't know, not everyone knows that if the two pictures are radically different, there's no way you can fuse them. Right? In that case, you have actually computation. So in this case, this animal, look at two pictures, they're very different. There's no way you can fuse them into a 3D image. So what happens is that perceptually, you only see one. In this case, the animal just sees this sort of this wheel-like pattern. But this percept also is switched spontaneously, right, based on the internal dynamics. So you can ask animal to report the percept by training animal to see something, like a target like this, you just push the lever, and you just report what you are seeing. Because they are not a human, they don't know. Then you give them some food for encouragement. But the question is, because the information goes to the two eyes are the same all the time, right? Your left eye always sees one, your right eye always sees the other all the time. There's no difference. The difference was happening inside the brain. But the question is at which level? So if you record from a neuron, let's say from LGN, lateral genicular body in the thalamus, it's guaranteed that it's just driven by only one eye. So no matter what you switch in your perception, the information goes to your eyes the same all the time, right? So it might be higher up, but at which level? So if you go to V1, you record a neuron neurons, they don't care about what you perceive. Just whatever information is there is always responding the same way. It doesn't matter what you actually see. You go higher up in the cortex, it starts to more represent what's the animal perceives. So this is one neuron in some visual cortex. This shows the firing rate of a neuron, the function of time. So the little bar underneath it is animal's report. Animal report is the red one. Maybe you see this pattern on the right. The white one, the yellow one is see the other pattern. So the activity neuron, you see, it goes up mostly when the animal sees this one of the other pattern. Right? So that's sort of this happens really at higher level in the cortex, right? In the visual cortex. So these activity correlated with the perception. You say this is just like a stupid animal, it's not human. But human people did similar work. In human, there are two different areas. I mean, you learned that in the visual lecture. There are some area in the brain that likes human faces. Right? To respond to faces, they're very specific. We can even respond to a particular individual, like Jennifer Aniston cell. Have you heard of Jennifer Aniston cell? I'll give a cover in my future lecture. It's just totally amazing. There's some neuron devoted just to that particular individual. Actually, you can. So there's a face area in the brain. So those areas, they're highly selected to faces. You never see human faces, they will act up. So some other parts of the brain, like especially area close to the hippocampus, they care about like spatial location. I'm going to cover that in my future lecture. So when you see the two images, one is a face, another the house, the two different brain areas are competing against each other. So human can do the similar experiment. Whenever you see the house or see the face, you can report. Human can push button and do the similar experiment and use functional magnetic imaging. You see the activity. Two different things like a push-pull, kind of similar to this. Really, the activity of the brain can predict what the human's the perception in a trial-by-trial basis. So that's really very similar. That's really what's happening in the brain will determine what you actually perceive, even though the information at a low level is exactly the same. Right? So this is a sort of you cannot do this with the feed forward network. It doesn't make sense, right? What you may imagine is maybe the eye get tired. It's not the case. Even you switch the image very quickly between the two eyes randomly, so you don't know which image comes from which eye. You still have the same kind of rivalry. So the information happens at a much higher level. It's not at the low level at all. All right. So second topic is about this oscillation. And just very briefly, only give you an example, the simplest possible example about oscillation. So oscillation happens a lot in the brain. You all know about EEG, right? EEG, when you get the electron in your head, you have any like oscilloscope, anything that's sensitive, you will see the activity in the brain. It's very easy to measure. So those basically. If you have neurons that connect with each other, it's very easy to get into this oscillatory state. If you have a spiking neural network model, it's actually very hard to make the system act in a graded, smooth manner. It's very easy to get a synchronized oscillatory pattern. It's basically like a seizure. It's very easy to get that. So it's a miracle that we don't get seizure all the time because there are lots of mechanisms to push things down. So if you have the simplest model, like say you have one excitatory group of cells, E, another inhibitory group of cells, or the inhibitory group of cells inhibit itself and inhibit the excitatory group. Right? Excitatory itself or excite itself and also excite the other group. That's a simple possible system. And you write the equation that looks like this. It's like similar to a perceptron. It's like so the information received by the E. So basically, it's all the inputs, the last two terms, right? So this is G is a gain function. The transfer, the E is activity of the. You can think about the memory potential of the excitatory group. It goes through this gain function. Basically, like we said last time, is basically transfer that into a firing rate. That's output of that cell, right? So this output of the excitatory cell. So this GI is the output of the inhibitory cell. So they pass through their connection, right? The synaptic weight. So the whole thing here, the sum is the total input to the excitatory cell, right? From itself and from other cell. So you have this sort of decay term that's a standard capacitor, like a resistor circuit, right? And the I is just external inputs from outside. If you have actual input from outside, it looks like this. This is a very simple system. For this system, if you don't do anything, they're actually depend on the parameter. Basically, all the connections, 4 different possible connections here, depend on the connections, you can do mathematical analysis to see what kind of behavior they have. For a two-dimensional system, you know what's the most complex behavior you can get out of a two-dimensional continuous dynamical system. You can get chaotic behavior? No, right? If you have a continuous system, you have to at least a three-dimensional. A two-dimensional system, the most complex behavior you can get is limit cycle oscillation. So in a simple case, it would be there's one is a sort of a fixed point sort of state. You start from random initial state here. There's an exciter inhibitory cell. It will have raining a little bit. Eventually approach stable states, right? So this is a. But if you use different parameters, this is one possible parameter. There's one possible behavior. So basically, the excitatory group, inhibitory group of cell, they eventually reach some kind of equilibrium and then stays there forever. So they're stable to the equilibrium point. So other parameters have limit cycle oscillation. So in this case, you see the excitatory inhibitory group there. There's some transient behavior, but eventually get into some stable pattern of oscillation. So the condition, I'm not going to go into mathematics of this. This is just a standard linear dynamical system analysis. It's very easy to do numerical experiment on this kind of system. So if you plot the states as in a phase plane, so basically the point on this plane is this axis, horizontal axis, is the excitatory states, E. The vertical axis is inhibitory states. Start from the states. Of course, all the arrows will be the derivative. That based on that dynamic equation, you know which direction the system is actually moving. So basically, the vector would be time derivative of E versus time derivative of I. Right? That's all the arrow. So that means you start from a state, it will follow the local arrow, it go spiral into this state. If you start from the inside, it will spiral outwards and it will approaching the same pattern activity. So if you only look at the one variable like E in time, it's just oscillatory this way. Right? The I will oscillate the other way. That's exactly the same as this, except for you plot it different ways. Right? So this is basically the simplest. There's a two excitatory cell, inhibitory cell. They can have this kind of oscillatory behavior, right? Depending on the parameter. So this is very like a brief discussion of an example of the simplest oscillator. Right? So now I'm going to talk to you about a fully connected recurrent network. So before I move on, is there any questions so far? Any questions? Okay. So the typical example is called the Hoffield network. It's proposed by John Hoffield. He was at Caltech, but he's at Princeton right now. The system is very simple. That you just have a bunch of neurons that's here. To show that it looks like a pyramidal cell. As I said, each neuron has a lot of inputs here. There's only one output. There's one axon. This axon go to many other cells, and they may contact other cells, may skip them on other cells. It's all possible, right? So basically, there's a bunch of neurons. So several of them. Their outputs all go out. They connect to themselves. It's like a self-connected. Just a simple network. It's very simple. So this system has a very interesting purpose. If you wire them up in a very in a clever way that I'm going to discuss in a moment, the system will behave like that. Let me just first show the behavior and then see how the system can be done. Right? You see how, whether the system is actually interesting. So in this case, what you present, there are many neurons. There may be thousands of neurons. So each pixel is activity. They represent activity of a single neuron. The neuron is very simple. Either you can use on-off, the binary cells with some probability of switching, or you can use sort of like a perceptron that we can use. Either discrete dynamics, everything upgrade together, or use continuous dynamic. Either way. In this case, so basically each pixel is the state of a single neuron. Right? So the system is wired up in a way it remembers many states as a memory pattern. So in this case, it remembers three: the spider pattern, bottle, and dog as a memory pattern. So it's very similar to the optimal linear mapping I showed you earlier, except for that, just a simple feed-forward. Here you go back to yourself. So here you see that if I start with some random initial pattern, but with some resemblance to the stored pattern, that pattern will be recovered. So this is the initial state. It evolves on its own without any input from outside. Right? Eventually, it will settle into that state, which is your remember state. So if you only show part of the figure, it will recover the other half, and eventually recover the full pattern. Just show just the ear, you can recover the whole dog. Is that interesting? That's very simple. So what is amazing about this is that, of course, it has some brain-like features. Right? If I show you only part of the figure, you can show me the whole thing. Sometimes you say, okay, what's that guy's name? I can't remember that guy. I know this guy. He was in maybe the football team or whatever. You give some feature, other people say, okay, that guy must be John or whatever, right? So sometimes you give you partial information, you can information. But in real memory, it's like that. You don't show me the full thing. If I should name some person, you remember, you say Obama, you can remember lots of things associated with Obama, good or bad, right? So the real memory sort of work like this. So this is a very simple artificial system, but it's already behaving in a way that you can recover memory just giving you partial cues. So what's perhaps most amazing, different from the standard traditional AI, is that it is very robust against noise and damage. So against noise, so here you can already see that if I have an image with a lot of arbitrary noises, this will be automatically cleaned up, right? You can clean up the noise automatically. It's very easy. So once you recover the final shape, there's not a single pixel of error. So that's a beauty. It's not like if I do filtering, I sort of make this noise inconspicuous, but there's still a little bit of there, right? But in this case, there's none, zero. So completely recover your stored pattern. Everything else would completely disappear, right? So what's against damage? The damage means this is fully connected network. You have neurons, everybody potentially connect with everybody. So if you cut the wires and you make the connection just disappear, you cut them or you change them, either increase or decrease in a random manner. You can maybe cut half of all the connections or even more, like 80%, or you can really damage a lot. So only the 20% connection remains, you still can do this kind of work, right? You may imagine if I damage like half of all the connection, maybe you can recover the memory. Maybe the memory is sort of screwed up a little bit. Just like you see like a sci-fi movie, the memory sort of a lot of blurred or something. But in this case, if you cut half of the wire randomly, the thing will recover the pattern, and the recovered pattern will have zero error as every pixel is correct. Is that amazing? It's without any error. Believe it or not, so I'm going to give you a homework on this coming Friday. You can play with it. You can convince yourself it really works that. It can work that way. And so how do you learn all these patterns? It turns out it's very easy. You can learn it in one shot. Just show it once as you remember it. That's it. And you can learn new pattern on top of something. You say you already stored these three patterns, so I have another one to remember too. You can do that very easily. Right? So how does this work? This is the simplest case. This is first show you the discrete dynamics. So you have a bunch of units, just like a neuron. So you have a state xi. It's from, in this case, simple case, from +1, -1. Simplest case, right? +1 means active, -1 means quiet. Right? It cannot be simpler than this, binary. In this case, the dynamics of system is updated this way. You should learn. This looks like a perceptron. Right? This Wij is a connection from unit J to unit I. Right? That's just convention, right? So this is activity unit J. So this term, you say that all the contribution from all the cell J to a fixed unit I. That's basically the sum of all the input to that particular cell, right? So then you go through a gain function. Here it is simple, like a sine, just like that's one of the sigmoidal, extreme case, right? Just either on or off. So if the total input is positive, the next time t + 1, you just +1, right? If the total input is negative, it is -1. That's very simple. Then you update all the cell like this. That's extremely simple. Right? The weights just are fixed. So the continuous case will look like this. So you have this the time derivative. There's one term that's like a standard CR circuitry, the RC circuitry, and it's just like exponential decay. Plus, you have all the inputs to the cell I from J, right? So all other cells to that particular cell. Right? Because this equation about cell I, right? So basically, weights all the connection from all possible other cells to the cell I. Of course, this is this is already passed through that gain function because you want the output of your firing rate and goes through synapse to affect that cell. The U you can think about as a membrane potential. Okay, so when the system reaches equilibrium state, all right, the time derivative of t doesn't work anymore. The system is settled into stable state. If that case, you get this equation like this, right? This equilibrium condition. So if you apply the gain function, you get this. The output of neuron I equal to this. So this, you look at this, you compare with this. That's exactly the same form, right? So if you have a discrete network like that, use the same gain function as continuous, their equilibrium state is actually identical. The time, evolution looks slightly different, but the final state is actually the same. So what's the learning rule? The learning rule also very simple. So you want to store a memory pattern. So the pattern would be, you can show it as a picture or whatever, just different pixel, each neuron either on or off. That's a pattern, right? So I have a list of +1, -1 for each of the neuron in your network. That's a memory pattern. If I want to remember that one at a stable state, what you should do is just use Wij from J to I, just equal the product of the two states for units I and unit J. So because each one is either +1 or -1. So if the two states are identical, either +1 or -1 at the same time, so this your weight is the +1, right? Otherwise -1. That's it, right? If you just do this, then the system will remember this state here as a stable state. You start from random inner state, it will settle into this state as stable states. So I'm going to show you a little bit about this biological meaning of this. So this is sort of called this, it's a very important theoretical idea called the Habs learning rule by Donald Hebb in this book, 1949, a very old book. So basically he said that if an axon is near enough to excite a cell B, and repeatedly or persistently takes part in firing rate, then some process will happen. You make the efficiency of A to firing B increased. So basically, a simple way to say this is sort of fire together, wire together. So if the two cells, they tend to fire together, they excite each other, so their connection should be strengthened. So the simplest form of this Hebb rule is written like this. So if you have two neurons, this is for neuron J, there's a synapse to neuron I. All right. So the simple mathematical form is extremely simple. So you change the weight based on the product of the two activities. So here, if the activity is just from 0 and 1, 0 means not active, +1 means active, this formula will be appropriate. This term, one of the cells not active, product like a logical AND, right? Both must be active at the same time. Then you have something that's going to happen. So you have an increment of that weight. Right? So it's like a logical AND. So both has to be active. Only one side is active that will work. So this is quite a simple Hebb. So this is very similar to this. You see, in mathematical form, look very similar to this, except for there's this. I ask here the +1, -1, not from 0 to 1, right? So it's not exactly right. But some people, say if instead of I say the activity 0 or 1, it's activity relative to some average value in the past. What do you mean? It's more if you're more active versus less active, you should have some learning to look like this. There's some people propose that. So I'm going to talk more about learning rule. The real biological learning rule, as you learned about LTP, LTD, all those stuff, it's much more complex than this, and also timing dependent plasticity. But this is the simplest idea to capture the most basic mechanism for learning, that you have to be different, have to be activated about the same time. But actually, the exact timing actually matters, right? But it's important to activate together. Then you can increase the weight. But for this learning, we don't, we're not saying this is exactly correct, not exactly correct, it's sort of a correctness. But because in this case, if both cells are quiet, in this simple formula, nothing will happen. But in our learning rule, if both are quiet, you also increase the weight. So there's a slight difference. It's more like this kind of, you manage some kind of background activity. So what do you need to do if I want to remember more than one memory pattern? So remember one pattern, you just say that, look at this, just like a product of the two, very easy. If I remember a second memory pattern, like say, I use a prime to denote the second pattern, just a bunch of +1, -1, a vector. Then you just add the second term on your weights, that's it. Extremely simple, right? So you can imagine that if I do learning, if you show me the pattern once, I just strengthen the weights according to the product. Then you show me a second pattern, I change the weights again by adding that term. Then you can remember all different patterns out there. But the problem is that the interference, if I remember something new, will that interfere with some stuff I already learned in the past? It will interfere unless they're statistically independent. That means if the second pattern, as if you draw from, flip a coin to say whether my picture should be on or off. So second pattern, you flip coin again to get a second pattern. In that case, they're independent. They're almost orthogonal to each other. In that case, it's not guaranteed not to have interference, right? So if it's hard to remember stuff, it's sort of similar, they're slightly different. In that case, it's harder. You have to use that pseudo inverse rule we talked about last time to do the weights. In that case, that should work, right? But that's a more advanced topic. Let's take a look at the simplest case and see how the system is supposed to work, all right? So first of all, let me show that if you have remember a bunch of patterns, well, first to show that if my initial state is exactly one of your remembered memory patterns, then the system will stay there. Now, that's the simplest thing we need to show first, right? Then we will see why if I have a pattern, maybe only not exactly the same, why the things will still work. So if it's exactly the same, right, I just say that you have a this Wi, that's a weights, the times the actual state, that's a total input to I, right, neuron I, all right? So here, I just wrote this, the W is actually, as we said before, is a bunch of memory pattern you remember, all right? So you just work this out, right? Just time all the stuff and show this here. You see the first term. The first term is that your pattern that's based on our assumption. It's one of the memory pattern. It's the same pattern as stored in there, right? Because of that, this xj times xj, because this is +1 -1, the xj squared is always equal to 1. We suppose we have a number neuron supposed to n, right? So this term would be s times n here, right? Because that's a matching term. So the other term over here is this other memory pattern you remember. It's based on our assumption, we assume it's sort of as if it's a memory pattern drawn statistically independently from some random process. In that case, so you see this thing could be, it's all +1 -1, but it could be +1 or -1 with equal probability, right? Because the two patterns are independent of each other. So in that case, it's sort of cancel each other out, right? So basically, you remember a bunch of memory patterns, but when you do this product, when you see what's the result, only the thing that matches the actual inputs will have a big contribution, right? The other term, because they are independent based on assumption, the ± tend to cancel out. It's a much smaller term. Right? So from here you can see what happens if my states, like say this SI is not exactly equal to the remembered state. Maybe 50% similar, another 50% just random. If that's the case, you do this, you see this about instead of n, you get half of n. Right? It's still this big term. So what matters for the next stage is that the total input here to I is positive or negative. Well, all this other term, this noise, very small. So most of this term, whether it's n or half n, doesn't matter. But this is really the sign determined by SI. That's a positive negative. So because of that, that's why if you have a lot of noise in there, as long as you're not, bigger, as long as it doesn't change the sign, right? It make no difference. That's why it still works perfectly. To show that, because it's harder to show that way, to show if the weights are not exactly like that, and you add a lot of noise, even the half of the noise, so the term here only about half the sign, but still it doesn't change the sign, right? As long as this term is much bigger than the noise term following it, then that's always fine, right? That clear? All right, so I think the only thing I need to show is that what is the square root of n? Is that all the noise term you add together, it increases not as the first term increase proportional to n, the other square root of n is much smaller. So this is, I'm sure you have heard of this, this is like a random walk, right? We call this, right? If someone, it looks like a stock market, right? If someone start from here, so in time one, you just either step forward, step up, or step down with equal probability. So this red line would be like a one instance, right? One realization of the stochastic process, just drunken working, step forward plus one minus one. So there, if you show many of them, so on average, of course, it's 0. But they're going to be further and further away from 0, right? So how farther away from that? So the standard deviation is just square root of n. That's a standard argument, right? So that means if I add up a bunch of terms like this, each of the product here is plus or minus 1, right? By assumption, they are random, plus or minus. If I add n terms, there's standard deviation of square root of n. So if your network is large enough, the n will be much bigger than square root of n. That's how the system works. So the trick to show this is very easy. That you have your sum a bunch of terms, xi's plus 1 minus 1. You consider on average it should be equal to 0, right? The error. But it's a standard deviation. If you just work out this, you can show. You have a square that shows either the square term versus all the cross term. The cross term, of course, going to be plus or minus, independent of each other, different as I, as j. So if I do averaging, average equal to n. So that's very easy to show. So the standard deviation must be equal to square root of n. So that's just a simple scaling argument. Okay. So let me just show you a little bit about the vector notation. So what you're going to is your use like a vector notation. So if you use, given this vector A and vector B, you assume it's a column vector by default. But the inner product, of course, should look like this. It's a scalar, right? There is nothing called outer product. It's like A times B transpose. And look at this, a matrix. The matrix is rank 1. It's just only only one vector that's all linearly dependent. So it's outer product. So this learning rule we showed you before is really it's an outer product rule. So you see what's this? Yeah. So we basically, so each of the memory pattern we showed Wij equal to each term, but if you show different memory pattern here, it should look like this. Right? It's different. It's outer product. You add up a different memory pattern. So basically it shows that different memory pattern, if you have an inner product, if they're the same, they're equal to n. If they are not the same, they're almost equal to 0. Right? That's like almost orthogonal to each other. Right? In that case, what you show is that, I showed you earlier that if you times this weight times this state is equal to proportional to the state itself. So in linear algebra, you would say that this state is an eigenvector of this matrix, the weight matrix. Right? So basically what the half-wave network does is that they embed a lot of states. The memory states correspond to dynamically stable equilibrium states. So these states turn out to be the eigenvectors of your connection weights. Right? So if you, in the future, suppose the Connect Home project is successful, so you can measure the connection in the individual brain, how different cells connect with each other. So you go to the memory area, like hippocampus or some area, you know the connectivity of all the cells, Then the simplest I would say, just do an eigen decomposition of that state, right? Then you can recover what's actually stored in that brain, even if this person already died a long time ago, right? As long as the connection is there, you can recover it, right? If this theory is correct, then you can see what's actually embedded in there, what's actually learned. All right, so. So is the question so far reasonably clear? Right. So here's your summary. You have each memory state is a stationary. That means if you go to that state, it stays there. Right. Second, the different memory patterns that are independent. If they're independent, then they can store in the same network without much interference. But of course, there's a limit. If you restore many of them, even though each of them contributes square root of n, if you have many of terms adding together, eventually it will be too bad. Right? It turns out for this system, about like a 14%, you can store memory patterns over 14% of the total number of neurons. That's still a lot, right? Yeah, this is also stable, that you perturb the pattern to go back. Okay, that we already said that informally. So this robotics against noise damage, we already mentioned that. So this is basically, it's a very interesting feature. So that's why the neural network is very interesting to people, is that really it's automatically will correct all the noise, right? Because it's a collective phenomenon. So if a cell fires, next time start wide fires, because we receive lots of input. Receive a lot of input from many other cells, right? If you see the damage, lot of connection, but if half of them still remain, they are pointing in the same direction, that's good enough to make me fire. Well, if I fire, then I'm 100% correct, right? So what's how strong the strength doesn't matter. You press a keyboard, some people hit the keyboard very big force, they just either on or off, right? As long as enough to push it, that's all it takes. There's an interesting concept about this called the energy function or Lyapunov function. So the idea is this: I can define a function. It's a scalar, right? It depends on the state. Okay? Given any time, time state, I can form this quadratic form based on the connection weights and the actual states. Then the whole thing is a scalar. It turns out this function, if there are no input, just system evolve on its own, it turns out it can always decrease. It cannot never increase. The system, of course, this function, it is bounded from below, that it cannot be negative infinity because it's all plus 1 minus 1. You put it together, in the worst case, you have some value, right? So if you always decrease, eventually you will stasis at some point, right? So those are, turns out, you see this quadratic function is minimized, if you remember your linear algebra, it's minimized if you constrain the norm or your vector, it minimized or maximized as some eigenvector, right? So the conceptual picture will look like this. So the height would be the scalar function, your energy or the Lyapunov function. So the plane would be your states, different states, right? So the system will, your time evolution system will look like a ball, like a marble, rolling spontaneously in this landscape. It will fall into some stable state. So each of the stable states is called a point attractor because it is a point in the state space, right? If you start from some location close enough to one memory pattern, it will fall into that state, to recover that state. If you are closer to a second memory pattern, fall to the second memory pattern. Right? That you can start from random initial state. This is sort of and go to one state. So this is sort of a conceptual picture of how the system works. Right? Is it clear so far? Anything still unclear? All right. So one thing I want to mention is that in a half-wave network, there's a symmetry. So if I look at the connection, say this, let me show, like this connection, it's always symmetric. The matrix of it is symmetric. So if I switch Wji, it's a product of two things switch, right? You multiply two things, the order doesn't matter. So that's with Wij is always equal to Wji. This is always true for this kind of system, right? It turns out this Lyapunov function works. It doesn't really require whether the weights is formed by product or not. The most important thing is symmetry. If you have a reciprocal symmetry, it's guaranteed to be stable, right? You all have this kind of property. So that can have very interesting application. I'll show you this is one application. Of course, first I have to emphasize that you're going to play with that in your homework. And if you delete the connection weights randomly, of course the weights, the resultant weight not going to be exactly symmetric, but it doesn't matter, the system still works. So basically, the symmetry condition is a sufficient condition to guarantee you have a Lyapunov function and a dynamical stability. Even if you are not symmetric, the system still works. I mean, this is sufficient, but not necessary. So there's one application, it's an old application, but I thought it's very interesting, so I want to explain to you a little bit. So you see the system, you already have some interesting protein recover memory. Can you do something else? Here is very interesting. It's to do an optimization problem. This is by Hatfield and Tank many years ago. But I saw the concept very interesting. The actual problem doesn't matter that much. But this is a sort of a traveling salesman problem. It's one of the combinatorial problems. It's a hard problem, right? So if I say, you have a bunch of cities, then find a path that goes through every city. So the total length is as short as possible. The traveling salesman problem. So if there are cities, it's very trivial. How to solve it. But if there are many cities, it's getting harder and harder. So this kind of problem, there are a bunch of this problem like this that depend on the size. As the problem size increases, the number of searches is increased exponentially. Right? So basically, in the worst case scenario, there are no better solution than just try everything exhaustively. It's a very hard problem. So the Hatfield Tank had a very interesting idea. What they show is that let's embed the problem in the network. So this is they show here is sort of a state, a bunch of networks. How many? Just like 10 by how many? So each pixel here is one neuron. All right. The square side means activity. All right. What are they coding that? They want to say that this is the city A, B to J. There's a bunch of cities. This is the order of the city, and it means that the first city, 1, should be D. You start from D. The second one should be H, and so on. Right. So what they did is that they use the weights. It turned out to be symmetric. It's such that each row and each column has only one cell should be active. You can design the weights in the clever way to make sure this will actually happen. And then the total weights would also be optimized. Right? So they basically use the weight somehow in the system optimize the Lyapunov function. That Lyapunov function is a problem you want to optimize. It turned out it's actually possible. So I'm not going to talk about the detail. Detail is kind of tedious, but it's ultimately not important for our purpose. But if you do that, the system, when you start from initial state, automatically find the states like this very fast. So this system will converge no matter what's the size of how many cities you have, converging in about the same time. It's a membrane potential time. 50 milliseconds and 50 milliseconds, 100 milliseconds, it's about that, no matter how many cities you have. But how good is the solution? The solution is not guaranteed to be optimal, right? So this is their simulation. So this is a histogram of all possible lenses of a particular, I'm not sure, it may not be this one, with a particular problem. So most of the stuff is very, it's like Gaussian distribution looks like. It's all possible routes passing through all the cities. There's many of them. many combinations, right? So the best possible one would be this arrow over here. It's much better than the bulge. This is really outstanding. So the network very quickly can find the solution over here. There's two stars here, the two different solutions found in the system. So the system can quickly get a good solution. It's may not be the best, but much better than many other solutions. So I thought this is a very interesting example. Right? If you have a function, the Lyapunov function system is stable, it automatically spontaneously tries to seek a local minimum of that system. So if you embed the problem in a clever way into the connection weights, maybe the system can be used to do an optimization problem, right? So if you solve like a perception and recognize an object, for engineer, usually you think about some error function or some criterion function you want to optimize. So that's general for many problems. So if you can embed that problem into your neural network, then the system may optimize it automatically. Right? This is the actual problem. I'm sure there are better algorithms than this, but I say the concept kind of important. Yeah. It's very interesting. Maybe the brain actually do stuff like this, because we come up with solution very fast, except for very logical stuff. If I have to compare logically and have to do sequentially, it's very, very slow. But other than that, I look at the person, I immediately recognize this guy is dangerous, right? It's, that's very quick, right? You'll come up with a solution very quickly. So I thought this is a very interesting example. So any questions? All right, I think that's all for today. Thank you very much.